Today we will discuss linear approximation. The basic idea is that for a function y equals f of x, near the point of tangency, the tangent line is a very good approximation to that function. So what we will do is near the point of tangency a f of a, we will replace y equals f of x by the tangent line, and using point slope, that gives us y minus f of a equals m, which is the derivative at a times x minus a. So we have that listed up here, and the idea is the right-hand side is a good approximation for the function f of x near the point of tangency. And we're going to give that function a name. We're going to call it L of x. So y equals L of x gives the equation of the tangent line at x equals a, and the basic idea is it's an approximation to the function near there. L of x depends on a. It is called the linearization of f of x at a. So for example, if f of x is the square root of x, let's find the tangent line and the linearization of f of x at x equals 4. Okay, so the first step is to look at the function and calculate its derivative, which is going to be the slope we're going to use for our tangent line. So f prime is 1/2 x to the minus 1/2, which can be written as 1 over 2 root x. Now, we want our tangency at a equals 4, so we get that f of 4 is the square root of 4, or 2, which is f of a, and f prime of 4, which is going to be the slope of our tangent line, is going to be 1 over 2 square root of 4, which works out to be 1/4. So our tangent line, y minus y naught equals mx minus x naught, becomes y minus 2 is 1/4 x minus 4. And we can write that as y equals 2 plus 1/4 x minus 4, and this is L of x, the linearization of f of x at x equals 4. And that approximates the function near x equals 4. It's important to note that this approximation is good near the point of tangency, but not very good elsewhere. So for example, if we look at the square root of 3.9 and use a calculator, we get this number. L of 3.9, this is replacing the square root by the linearization, is 2 plus 1/4, 3.9 minus 4, which is 2 plus 1/4 times minus 0.1, which is 2 minus 0.025, which is 1.975. So the linearization gives us this approximation for the square root of 3.9. And if you look at these two values, you can see it's really good. The error in the approximation is only 0.00016, and the relative error, which is sort of take the error and divide it by the actual value, and you get sort of a percentage error, and here the percentage error is 0.0081%, which is very small. Now, if we were foolish enough to try to use this approximation to find the square root of 1, well, the square root of 1 is 1. L of 1 turns out to be 2 plus 1/4, 1 minus 4, which is 2 minus 0.75, which is 1.25. The error in that is 0.25, which is 25% of the value. So this is a very bad approximation. So the message here, don't use linear approximations except near the point of tangency. Okay, now what we're going to look at is the idea of a differential. So here's a picture of our y equals f of x. Here's our point a, f of a. And we look how the function changes, delta y, as the x value changes. And what we're going to do is replace that delta y, which is the change that we get because x changed, by the change along the tangent line. And we're going to relabel these things. Dx is going to be the change in the x direction, and dy is the change you get not because of f of x, but because of our approximating tangent line. So we're thinking of dx is a little change in x, dy is a little change in y, and their slope is the slope of the tangent line, and the slope of the tangent line is f prime of a. So dy divided by dx is f prime of a, and what we're going to do is define this thing called the differential at x equals a, and we're just going to multiply through by dx. So we have dy is f prime of a dx, and that is the differential of f of x at x equals a. The general differential is what we would get if we didn't actually specify the point of tangency. So that's going to be just dy equals f prime of x dx. You take this expression, substitute in x equals a, and you get the differential at a. So for example, if y is x cubed plus 3x, the differential is dy equals, and now this is the derivative of y, which is 3x squared plus 3 dx. And if we want the differential at x equals minus 1, we just put minus 1 in here, and we get 3 times minus 1 squared plus 3, which is 3 plus 3, or 6 dx. So dy equals 6 dx is the differential at x equals minus 1. So for an example, let's use the differential at x equals 4 to estimate how much the value of y equals square root of x changes from 4 to 3.9, and this should look familiar. It's the calculation we've done previously. F of x is x to the 1/2, so the derivative is what it was before. The differential is just dy equals 1 over 2 root x dx. A is 4, which is where we're trying to estimate this thing. So f prime of 4 is 1 over 2 square root of 4, which is a quarter. Means that our differential becomes dy is 1/4 dx. X changes from x equals 4, the value at the point of tangency, to x equals 3.9. So dx is 3.9 minus 4, or minus 0.1. Okay, and that's important here. It's where you want to make the estimate minus where the point of tangency is. So our estimated change in y is dy is 1/4 dx, which is 1/4 times minus 0.1, which is minus 0.025. So another example. A solid metal sphere of radius 4 centimeters is coated with a spherical plastic shell of thickness 0.01 centimeters. Estimate how much plastic is used. We could use the tangent line approximation, or we could use differentials, and we're going to use the differential to do this. So the volume of the sphere is 4/3 pi r cubed. So dV is the derivative of 4/3 pi r cubed, which is 4/3 pi 3r squared, which is 4 pi r squared dr. Okay, now, coating the sphere with plastic changes its radius from 4 to 4.1, and that's going to change the volume. That change in volume is the amount of plastic we need. So we want to compute the differential at r equals 4 and take dr to be 0.1. So dV is 4 pi 4 squared dr, which is 4 pi times 16 times 0.01, which works out to be 6.4 pi centimeters cubed. And when you calculate that, you get approximately 20.1 cubic centimeters, and that's approximately how much plastic we need to coat the sphere. So let's do a final example here. Let's estimate 2 over the 4th root of 0.98 using L of x and differentials. And in the process, what we're going to see is that the two methods are really the same method. So first, we need a function for this. And it looks natural to choose 2 over the 4th root of x, because this is what you would get if x was equal to 0.98. Okay, so this is the function we're going to choose. And now we need a point of tangency. And x equals 1 is close to 0.98. And notice that the function is easy to evaluate when x equals 1. F of 1 is 2 times 1 to the minus 1/4, which is 2. Easy calculation. And this is the place that we're going to use as our x-coordinate of the point of tangency. Thus, the point of tangency is 1f of 1. And you notice here that f of 1 is 2 over 1, or 2. So this is our point of tangency. We compute f prime of x. And what we can see is the derivative of 2x to the minus 1/4 is going to be 2 times minus 1/4 x to the minus 5/4, which gives us minus 1/2 x to the minus 5/4. We put in 1, and we get that f prime of 1 is 1/2 times 1 to the minus 5/4, or 1/2. That's the slope of our tangent line. So our tangent line is going to be y minus 2, the y-coordinate, equals minus 1/2 x minus 1, the x-coordinate. And moving the minus 2 on the right-hand side, y equals minus 1/2 x minus 1 plus 2, which is what we've been calling L of x. And now we want the value of L at 0.98, which is minus 1/4. 0.98 minus 1 plus 2. This ends up being minus 0.02 times minus 1/2 is plus 0.01 plus 2, which is 2.01, which is what the linearization gives us as an estimate. If you use a calculator, you get 2.01013. So again, we're doing very well with this estimate. Now let's do it using differentials. Okay, so dy is f prime of x dx. X is 1. So dy is going to be f prime of 1 dx. And we've already calculated f prime at 1. It's right up here. It's a minus 1/2 dx. Now dy is going to be y minus 2, because dy measures the change in y from the point of tangency, which is 1, 2. And that means that dx is going to be x minus 1 for exactly that same reason. X changes from the point of tangency where it has a value of 1. And now if you plug that in, you get that dy is y minus 2 equals minus 1/2 dx is x minus 1. And if you move the 2 on the right-hand side, you get y equals minus 1/2 x minus 1 plus 2, which if you look up here is exactly what L of x is. So this calculation is pretty much the same calculation we just did. You pop in 0.98 and you get 2.01.